demos that will show you how to install and get started with Docker. And most importantly, we have hands-on labs that you can access right in your browser. I will explain more about it in a bit, but first, let's look at the objectives of this course. In this course, we first try to understand what containers are, what Docker is, and why you might need it, and what it can do for you. We will see how to run a Docker container, how to build your own Docker image. We will see networking in Docker and how to use Docker Compose, what Docker registry is, how to deploy your own private registry, and we then look at some of these concepts like Docker Swarm and Kubernetes. Here's a quick note about hands-on labs. First of all, to complete this course, you don't have to set up your own labs. Well, you may set it up if you wish to have your own environment, and we have a demo as well. But as part of this course, we provide real labs that you can access right in your browser, anywhere, anytime, and as many times as you want. The labs give you instant access to a terminal, to a Docker host, and an accompanying quiz portal. The quiz portal asks a set of questions, such as exploring the environment and gathering information, or you might be asked to perform an action such as run Docker container. The quiz portal then validates your work and gives you feedback instantly. Every lecture in this course is accompanied by such challenging interactive quizzes that makes learning Docker a fun activity. So I hope you're as thrilled as I am to get started. So let us begin. We're going to start by looking at a high-level overview on why you need Docker and what it can do for you. Let me start by sharing how I got introduced to Docker. In one of my previous projects, I had this requirement to set up an end-to-end application stack, including various different technologies, like a web server using Node.js and a database such as MongoDB, and a messaging system like Redis, and an orchestration tool like Ansible. We had a lot of issues developing this application stack with all these different components. First of all, their compatibility with the underlying OS was an issue. We had to ensure that all these different services were compatible with the version of OS we were planning to use. There have been times when certain versions of these services were not compatible with the OS, and we've had to go back and look at different OS that was compatible with all of these different services. Secondly, we had to check the compatibility between these services and the libraries and dependencies on the OS. We've had issues where one service requires one version of a dependent library, whereas another service requires another version. The architecture of our application changed over time. We've had to upgrade to newer versions of these components, or change the database, etc. And every time something changed, we had to go through the same process of checking compatibility between these various components and the underlying infrastructure. This compatibility matrix issue is usually referred to as the matrix from hell. Next, every time we had a new developer on board, we found it really difficult to set up a new environment. The new developers had to follow a large set of instructions and run hundreds of commands to finally set up their environments. We had to make sure they were using the right operating system, the right versions of each of these components, and each developer had to set all that up by himself each time. We also had different development, test, and production environments. One developer may be comfortable using one OS, and the others may be comfortable using another one. And so we couldn't guarantee that the application that we were building would run the same way in different environments. And so all of this made our life in developing, building, and shipping the application really difficult. So I needed something that could help us with the compatibility issue, and something that will allow us to modify or change these components without affecting the other components, and even modify the underlying operating systems as required. And that search landed me on Docker. With Docker, I was able to run each component in a separate container with its own dependencies and its own libraries, all on the same VM and the OS, but within separate environments or containers. We just had to build the Docker configuration once, and all our developers could now get started with a simple Docker run command. Irrespective of what the underlying operating system they run, all they needed to do was to make sure they had Docker installed on their systems. So what are containers? Containers are completely isolated environments, as in they can have their own processes or services, their own network interfaces, their own mounts, just like virtual machines, except they all share the same OS kernel. We will look at what that means in a bit, but it's also important to note that containers are not new with Docker. Containers have existed for about 10 years now, and some of the different types of containers are LXC, LXD, LXCFS, etc. Docker utilizes LXC containers. Setting up these container environments is hard as they are very low level, and that is where Docker offers a high-level tool with several powerful functionalities, making it really easy for end users like us. To understand how Docker works, let us revisit some basic concepts of operating systems. First, if you look at operating systems like Ubuntu, Fedora, SUSE, or CentOS, they all consist of two things: an OS kernel and a set of software. The OS kernel is responsible for interacting with the underlying hardware, while the OS kernel remains the same, which is Linux in this case. It's the software above it that makes these operating systems different. This software may consist of a different user interface, drivers, compilers, file managers, developer tools, etc. So you have a common Linux kernel shared across all OSs, and some custom software that differentiate operating systems from each other. We said earlier that Docker containers share the underlying kernel. So what does that actually mean, sharing the kernel? Let's say we have a system with an Ubuntu OS with Docker installed on it. Docker can run any flavor of OS on top of it as long as they are all based on the same kernel, in this case, Linux. If the underlying OS is Ubuntu, Docker can run a container based on another distribution like Debian, Fedora, SUSE, or CentOS. Each Docker container only has the additional software that we just talked about in the previous slide that makes these operating systems different, and Docker utilizes the underlying kernel of the Docker host, which works with all OSs above. So what is an OS that do not share the same kernel as this? Windows. And so you won't be able to run a Windows-based container on a Docker host with Linux on it. For that, you will require Docker on a Windows server. Now, it is when I say this that most of my students go, hey, hold on there, that's not true. And they install Docker on Windows, run a container based on Linux, and go, see, it's possible. Well, when you install Docker on Windows and run a Linux container on Windows, you're not really running a Linux container on Windows. Windows runs a Linux container on a Linux virtual machine under the hoods. So it's really Linux container on Linux virtual machine on Windows. We discuss more about this on the Docker on Windows or Mac later during this course.
Okay, I hope the discussion up to this point is crisp and understandable and things are audible. If so, please point to it in the chat window. If you have any doubts up to this point, you're free to ask them within next minute, or we'll continue the video further. Use the chat window to tell any queries if you have, or you want to have some elaboration on any particular point, or if you want me to continue further, I just write continue. I'll just continue the video. Should we continue? Yeah, thanks a lot. Require some
Now,
feedback.
you might ask, isn't that a disadvantage then, not being able to run another kernel on the OS? The answer is no, because unlike hypervisors, Docker is not meant to virtualize and run different operating systems and kernels on the same hardware. The main purpose of Docker is to package and containerize applications and to ship them and to run them anywhere, anytime, as many times as you want. So that brings us to the differences between virtual machines and containers, something that we tend to do, especially those from a virtualization background. As you can see on the right, in case of Docker, we have the underlying hardware, infrastructure, and then the OS, and then Docker installed on the OS. Docker then manages the containers that run with libraries and dependencies alone. In case of virtual machines, we have the hypervisor like ESX on the hardware, and then the virtual machines on them. As you can see, each virtual machine has its own OS inside it, and then the dependencies, and then the application. The overhead causes higher utilization of underlying resources as there are multiple virtual operating systems and kernels running. The virtual machines also consume higher disk space as each VM is heavy and is usually in gigabytes in size, whereas Docker containers are lightweight and are usually in megabytes in size. This allows Docker containers to boot up faster, usually in a matter of seconds, whereas VMs, as we know, takes minutes to boot up as it needs to boot up the entire operating system. It is also important to note that Docker has less isolation as more resources are shared between the containers, like the kernel, whereas VMs have complete isolation from each other. Since VMs don't rely on the underlying OS or kernel, you can run different types of applications built on different OSs, such as Linux-based or Windows-based apps on the same hypervisor. So those are some differences between the two. Now, having said that, it's not an either container or virtual machine situation. It's containers and virtual machines. Now, when you have large environments with thousands of application containers running on thousands of Docker hosts, you will often see containers provisioned on virtual Docker hosts. That way, we can utilize the advantages of both technologies. We can use the benefits of virtualization to easily provision or decommission Docker hosts as required, at the same time make use of the benefits of Docker to easily provision applications and quickly scale them as required. But remember that in this case, we will not be provisioning that many virtual machines as we used to before, because earlier we provisioned a virtual machine for each application. Now you might provision a virtual machine for hundreds or thousands of containers. So how is it done? There are lots of containerized versions of applications readily available as of today. So most organizations have their products containerized and available in a public Docker repository called Docker Hub or Docker Store. For example, you can find images of most common operating systems, databases, and other services and tools. Once you identify the images you need and you install Docker on your host, bringing up an application is as easy as running a Docker run command with the name of the image. In this case, running a Docker run Ansible command will run an instance of Ansible on the Docker host. Similarly, run an instance of MongoDB, Redis, and Node.js using the Docker run command. If we need to run multiple instances of the web service, simply add as many instances as you need and configure a load balancer of some kind in the front. In case one of the instances were to fail, simply destroy that instance and launch a new one. There are other solutions available for handling such cases that we will look at later during this course. And for now, don't focus too much on the commands. We will get to that in a bit. We've been talking about images and containers. Let's understand the difference between the two. An image is a package or a template, just like a VM template that you might have worked with in the virtualization world. It is used to create one or more containers. Containers are running instances of images that are isolated and have their own environments and set of processes. As we have seen before, a lot of products have been Dockerized already. In case you cannot find what you're looking for, you could create your own image and push it to Docker Hub repository, making it available for the public. So if you look at it, traditionally, developers developed applications. Then they hand it over to ops team to deploy and manage it in production environments. They do that by providing a set of instructions, such as information about how the host must be set up, what prerequisites are to be installed on the host, and how the dependencies are to be configured, etc. Since the ops team did not really develop the application on their own, they struggle with setting it up. When they hit an issue, they work with the developers to resolve it. With Docker, the developers and operations teams work hand in hand to transform the guide into a Docker file with both of their requirements. This Docker file is then used to create an image for their applications. This image can now run on any host with Docker installed on it and is guaranteed to run the same way everywhere. So the ops team can now simply use the image to deploy the application. Since the image was already working when the developer built it and operations have not modified it, it continues to work the same way when deployed in production. And that's one example of how a tool like Docker contributes to the DevOps culture. Well, that's it for now. And in the upcoming lecture, we will look at how to get started with Docker. We will now see how to get started with Docker. Now, Docker has two editions, the Community Edition and the Enterprise Edition. The Community Edition is the set of free Docker products. The Enterprise Edition is the certified and supported container platform that comes with enterprise add-ons like the image management, image security, universal control plane for managing and orchestrating container runtimes. But of course, these come with a price. We will discuss more about container orchestration later in this course, and along with some alternatives. For now, we will go ahead with the Community Edition. The Community Edition is available on Linux, Mac, Windows, or on cloud platforms like AWS or Azure. In the upcoming demo, we will take a look at how to install and get started with Docker on a Linux system. Now, if you are on Mac or Windows, you have two options. Either install a Linux VM using VirtualBox or some kind of virtualization platform, and then follow along with the upcoming demo, which is really the most easiest way to get started with Docker. The second option is to install Docker Desktop for Mac or Docker Desktop for Windows, which are native applications. So if that is really what you want, check out the Docker for Mac and the Windows sections towards the end of this course, and then head back here once you're all set up. We will now head over to a demo, and we will take a look at how to install Docker on a Linux machine. In this demo, we look at how to install and get started with Docker. First of all, identify a system, physical or virtual machine, or laptop that has a supported operating system. In my case, I have an Ubuntu VM. Go to docs.docker.com and click on Get Docker. You will be taken to the Docker Engine Community Edition page. That is the free version that we are after. From the left-hand menu, select your system type. I choose Linux in my case, and then select your OS flavor. I choose Ubuntu. Read through the prerequisites and requirements. Your Ubuntu system must be 64-bit and one of the supported versions like Disco, Cosmic, Bionic, or Xennial. In my case, I have a Bionic version. To confirm, view the etc release file. Next, uninstall any older version if one exists. So let's just make sure that there's none on my host. So I'll just copy and paste that command. And I confirm that there are no older versions that exist on my system. The next step is to set up repository and install the software. Now, there are two ways to go about this. The first is using the package manager by first updating the repository using the apt-get update command, then installing the prerequisite packages, and then adding Docker's official GPG keys, and then installing Docker. But I'm not going to go that route. There is an easier way. If you scroll all the way to the bottom, you will find the instructions to install Docker using the convenience script. It's a script that automates the entire installation process and works on most operating systems. Run the first command to download a copy of the script, and then run the second command to execute the script to install Docker automatically. Give it a few minutes to complete the installation. The installation is now successful. Let us now check the version of Docker using the docker version command. We've installed version 19.03.1. We will now run a simple container to ensure everything is working as expected. For this, head over to Docker Hub at hub.docker.com. Here you will find a list of the most popular Docker images like Nginx, MongoDB, Alpine, Node.js, Redis, etc. Let's search for a fun image called Whalesay. Whalesay is Docker's version of Cowsay, which is basically a simple application that prints a cow saying something. In this case, it happens to be a whale. Copy the docker run command given here. Remember to add sudo, and we will change the message to hello world. On running this command, Docker pulls the image of the Whalesay application from Docker Hub and runs it. And we have our whale saying hello. Great. We're all set. Remember, for the purpose of this course, you don't really need to set up a Docker system on your own. We provide hands-on labs that you will get access to, but if you wish to experiment on your own and follow along, feel free